today's November 13th. If you go to uahighrise.org, they posted pictures from Mars today, but they can't post these 3I Atlas pictures from October 2nd. So bizarre. How do you respond to that?
Well, we had 45 days since the images were taken, and there are people involved in the high-rise camera that are not government employees. Some of them are, affiliated with the University of Arizona. They definitely had plenty of time.
But Dr. Loeb, do you believe the NASA administrator? Do you believe the NASA administrator? Do you believe what he just said to me?
I have no issue with him. He's basically repeating what people are telling him.
Yeah, I don't either. I just want the truth.
Right. So I think we will hopefully see something coming out in the coming days, but it just shows you how sluggish is this system of bureaucracy. I don't necessarily think they are trying to do something, on purpose. It may be just bureaucracy taking over science.
I agree, and that seems like a whole lot of bureaucracy. Again, those photos taken October 2nd. It's November 13th. Dr. Avi Loeb, we will have you back. Good to see you again. Thank you.
A sudden and dramatic change in 3I Atlas has completely taken astronomers by surprise. In the newest series of telescope observations, this interstellar object has started growing its dust tail at a speed no one expected. Its entire structure is shifting faster and more aggressively than any scientific model predicted. What began as a weak, uneven plume has now turned into a sharp, bright, fully developed tail captured in a new set of high-resolution images. At almost the same moment, another surprising report began spreading through radio astronomy circles. A short, unverified radio pulse was detected near 1420 megahertz, the hydrogen line frequency that scientists constantly monitor in deep space surveys. The signal is still unconfirmed, but the timing, paired with Atlas's sudden burst of activity, has forced researchers to pay extremely close attention. Something about these two events lining up has made the scientific community uneasy. 3I Atlas, officially the third interstellar object ever recorded in our solar system, has been under routine tracking since the day it was discovered. For months, it behaved exactly how astronomers expected: dim, slow, cold, and almost featureless. A frozen leftover from another star system simply drifting inward at a steady pace. But in the past few weeks, its behavior has shifted in a way that defies the usual rules for objects made of ice from deep interstellar space. When exposed to sunlight, these bodies normally warm up slowly and release gas in predictable patterns. Atlas didn't follow that pattern. The first strange sign appeared when scientists noticed a plume pointing toward the sun, a shape almost never seen in comets inside our solar system. Typical comets push out gas and dust away from the sun, forming tails that stretch outward into space because of solar radiation pressure. But 3I Atlas did the opposite. It pushed material almost directly toward the sun, creating a short, uneven, forward-facing plume that confused everyone watching it. As Atlas traveled closer to the sun, researchers did expect some level of early activity. If its surface contained volatile ices, things like carbon monoxide or carbon dioxide, which evaporate at low temperatures, they assumed it would start to release gas slowly. But the way this activity unfolded was nothing like what anyone predicted. Early images revealed a faint, lopsided plume pointing in a sunward direction, a strange feature that didn't match any classic comet behavior. Instead of forming a trailing dust tail, Atlas looked like it was pushing material forward, as if something on the surface was releasing gas from a very specific vent, crack, or fracture. For several cycles of observation, this odd plume stayed the same. It didn't grow much and didn't break apart. It looked like 3I Atlas might keep this unusual shape all the way through its journey, a strange but steady characteristic of this interstellar object. Then everything changed almost overnight. When large ground-based telescopes in Chile and South Africa collected new data, the sunward plume had completely reshaped itself into a classic comet tail. Long, bright, and stretching directly away from the sun, just like comets normally behave. What shocked astronomers most wasn't simply the new shape, it was the incredible speed of the transformation. In a very short amount of time, the entire structure rearranged itself, meaning huge amounts of dust must have suddenly been released from the nucleus. Fresh dust analysis, based on photometric modeling and early spectroscopic readings, shows that the material coming off 3I Atlas is surprisingly large in size. Instead of the tiny micron-scale grains usually produced when water ice heats up, Atlas is releasing particles nearly 1/10 of a millimeter across. These grains are heavier and harder to move, which means the gas escaping from the nucleus is steady but not explosive, strong enough to push large grains outward, but only at speeds of a few meters per second. This slow, steady release hints at a nucleus that is either extremely dense and tightly bonded, or one that has layers of different materials reacting in different ways as sunlight heats them. Whatever the case, the behavior is unlike most comets in our solar system, adding a new layer of mystery to an object that was already unusual the moment it entered our solar neighborhood. Spectroscopic readings from 3I Atlas show something surprising. The object started releasing gas when it was still more than 3.5 astronomical units away from the Sun. At that distance, water ice should remain completely frozen. Only hypervolatile ices, like carbon monoxide or carbon dioxide, can warm up enough to sublimate that far out. These hypervolatiles are usually found in extremely cold outer regions of star systems. Their early release suggests that 3I Atlas carries a large amount of them beneath its surface. This strengthens the idea that the object likely formed in a region similar to our Oort cloud or Kuiper belt, but belonging to another star entirely, a distant, icy zone where temperatures stay unbelievably low for billions of years. Atlas may have spent most of its life in that frozen darkness until something disturbed its orbit and launched it into deep space, eventually sending it toward our solar system. The early plume and the fast-growing tail have already given astronomers plenty to study. But the situation gained even more attention when a possible radio pulse near 1420 megahertz was reported. This particular frequency, known as the hydrogen line, is one of the most carefully watched areas of the radio spectrum. Neutral hydrogen naturally emits at this frequency, and because it sits in a relatively quiet radio band, scientists use it to study the structure of our galaxy, star-forming regions, and the movement of massive clouds of interstellar gas. The hydrogen frequency is also famous for another reason. SETI, the search for extraterrestrial intelligence, has long considered it a strategic, universal channel. Many researchers believe that if any advanced civilization ever tried to send a deliberate signal, it might choose this frequency because every astronomer pays attention to it. The reported pulse was extremely short and detected by only a few observers. None of them have released a peer-reviewed study yet. It could have easily been a malfunction in equipment, interference from Earth, a passing satellite, or even a natural cosmic event unrelated to Atlas. The lack of confirmation shows how careful scientists are whenever such claims appear. But the timing makes it interesting. The pulse was recorded right when Atlas began showing major changes. Its plume shifting, its tail exploding outward, and its activity increasing sharply. That coincidence has encouraged many radio observatories to start follow-up scans. Their goal now is to check whether any repeating or stable signal exists in the region of the sky where Atlas is currently traveling. Right now, there is no evidence that the radio pulse came from 3I Atlas. But even unverified signals are valuable because they encourage deeper investigation. Major radio telescopes, both large interferometric arrays and single-dish facilities, are now reviewing data from the same time frame. Some will continue scanning the 1,420 megahertz band over the next several weeks to determine whether the pulse was a one-time anomaly or the beginning of a recurring pattern. Even if a repeated radio emission turned out to be entirely natural, unrelated to any artificial source, it would still be significant. Very few comets produce strong radio signals outside of molecular emissions. Detecting anything unusual would teach astronomers something new about how interstellar objects behave. Meanwhile, the physical changes happening inside 3I Atlas are far more crucial for understanding what this object really is. The rapid evolution of its tail gives scientists a rare chance to study how dust reacts to sunlight, how particles behave as temperatures climb, and how cracks or vents on the nucleus can sculpt the overall shape of a comet. In some of the latest images, tiny curves and changing brightness patterns are already visible along the tail. These may hint at multiple active vents on the nucleus releasing material in different directions. As Atlas continues moving inward, researchers expect even more features to appear: jets, waves, shells, or distinct dust layers that reveal how the interior responds to the growing heat of the sun. Comparing Atlas to previous interstellar objects shows just how unusual it is. Oumuamua, the first, never produced any gas or dust. Its brightness changed in ways that suggested a long, flat, or tumbling shape. It also experienced small, unexplained accelerations that didn't match the behavior of typical comets. That led to theories involving nitrogen ice, hydrogen ice, hollow fractal structures, and other exotic materials. The second interstellar visitor, 2I/Borisov, behaved more like a normal comet. It had a bright nucleus, a clear tail, and a steady release of dust and gas. Its chemistry looked similar to icy bodies from our own outer solar system. 3I Atlas, however, is breaking patterns and rules, showing behavior that is neither fully typical nor completely unprecedented, making it one of the most intriguing interstellar visitors scientists have ever studied. 3I/Atlas stands apart from both previous interstellar visitors. Its earliest plume looked nothing like Oumuamua, and its dust release pattern is completely different from 2I/Borisov. The grains coming off 3I/Atlas are unusually large and slow-moving, which does not match most comets in our solar system. And now, the sudden speed of its tail growth is far faster than what standard heating and sublimation models can explain. All these unusual features combined make 3I/Atlas one of the most scientifically valuable interstellar objects ever observed. Because 3I/Atlas is becoming more active by the day, astronomers are rushing to collect as much information as possible before it reaches maximum brightness, or before it breaks apart. Many comets fragment as they get closer to the sun, especially if they contain deep pockets of volatile materials, cracks, or weak internal layers. If 3I/Atlas were to split, each fragment would expose a fresh section of interior surface, which could help scientists study its composition more easily. But fragmentation also makes the original nucleus harder to track, as the pieces drift apart and evolve differently. Breakup events often reveal a comet's secrets. They can show layers inside the nucleus, differences in density, or the presence of thermal stress that can't be detected from the outside. Because of this possibility, observatories around the world are coordinating to maintain constant watch over 3I/Atlas. Optical telescopes are measuring brightness changes and modeling how the dust spreads. Infrared instruments are tracking the heat distribution across the coma. Spectroscopic systems are identifying the gases turning into vapor as sunlight warms the nucleus. Radio telescopes are checking for molecular emissions and scanning again for any unusual or repeating pulses. The collection of all these observations may become the most complete data set ever assembled for an interstellar comet, possibly even more detailed than what scientists gathered for 2I/Borisov. As new information arrives, researchers will refine their understanding of how 3I/Atlas produces dust and gas over time. The structure of its tail will help determine the comet's rotation speed and reveal which areas on the surface are actively venting material. Studying the coma, the cloud of gas and dust around the nucleus will show how sunlight is altering the material released from the interior. Even small shifts in brightness can hint whether the nucleus is elongated, irregular, or already developing internal fractures. But the evolution of 3I/Atlas is about more than just one comet. It's a chance to understand how frozen bodies behave after spending millions or even billions of years drifting through interstellar space. According to many theories, Comets are often ejected from young planetary systems when giant planets pull on them with strong gravity. Once thrown out, these icy objects wander between the stars for ages, getting hit by dust grains, cosmic rays, and micrometeoroids. Over time, their surfaces become hardened, altered, and chemically changed. When such an ancient object finally enters a new star system, like 3I/Atlas entering ours, the sudden warmth and radiation can trigger unusual patterns of activity, exposing layers that have not seen light for countless millennia. Observing those changes gives astronomers a rare look at processes that happened long before our sun and planets formed. The scientific community is watching closely as 3I/Atlas grows brighter and more unstable. Even if the reported radio pulse turns out to be unrelated, the rapid tail growth, the strange dust properties, and the early release of hypervolatile gases all point to a complex, layered interior shaped in an environment no one fully understands yet. In the coming weeks, as 3I/Atlas moves closer to the sun, its rate of change may accelerate even more. New jets may appear, the tail may twist or split, and unexpected emissions may show up in multiple wavelengths. Whatever happens, the transformation of 3I/Atlas is one of the most important natural experiments modern astronomy has ever seen. A small, ancient traveler from another star system revealing its secrets in real time. Each new observation adds another piece to the puzzle and brings scientists one step closer to understanding how interstellar material forms, survives, and evolves across the vast distances of the galaxy.